Now, the first example I'm going to do isn't using the ice yet, it's just to show you the contrast that exists here. If I got 100 grams of water at 0 degrees, I got 100 grams of water at 80 degrees. We mix these two together, it's going to be a true average. They're both water, they got the same specific heat. What we're going to end up with is we're going to end up with 200 grams of water at 40 degrees, right? It's fairly obvious to see. Okay, now if we just make one slight change, and I'm going to say this is, instead of water, this is ice. It's like water, okay? But it's different. That introduces an extra term. Once that ice melts, I'm going to have 100 grams of water. So I'm going to have this term, I'm going to have the term of the melt. Then I'm going to have plus the Q of the cold water plus the Q of the hot water. Now, where did the cold water come from? Well, once the ice melts, then it has to be heated up. If we just started there, we get to 40. Okay. But if we don't start there and instead we say, okay, we're going to go ahead and start with ice here. And I'm going to do this all, let's say we'll do this one in a styrofoam cup, so we're not going to have to worry about a calorimeter. We're going to say the calorimeter is styrofoam and we're not losing any energy to that. And that's a terrible assumption, but we're going to assume that anyway to keep the example fairly simple. So we've got the Q of the melt. Now I said it takes 79.7 calories per gram, and I've got a mass of 100 grams. That tells me how many calories it's going to take to melt that. That's eating energy from the system, okay? It takes that much to melt it. It's using the energy that's coming from the hot water, right? Now, the cold water, I've got 100 grams. I've got a C of 1. And delta T is going to be T minus 0. Now, if you look at this, we know we're going to end up somewhere between 0 and 80 degrees. T is going to be positive. Therefore, this term is going to be positive. The heating up water and the positive that's here, they both have to be positive because both of them are taking energy from the system. Some people do this and they reverse the T's the other way and they make them both negative. It's okay. They have to have the same sign. Okay? That's positive. That's positive. They are eating energy from the system. The other one, overall, the term has to end up being negative. We'll look and see if it will. We put in 100 for the mass. We put in 1 for the C. And we have T minus 80. And again, we're going to end up somewhere between 0 and 80. Therefore, that term is going to be negative. That's the one that's giving to the system. These are taking from the system. And we end up in an equilibrium place overall. So now, what do I have? Well, I go ahead and multiply some of this out. I got 7970 plus 100T. Of course, the 0 is nothing going on there. 100T minus that. And I've got 200T equals, and I've got slightly more negative than I've got positive here. That looks like I've got 30 over here. And T would be 0.15. Now, why does that look different than the example that I just gave? I don't know. I must have rounded off in my example. I don't think I missed anything here. So, what does this tell me? It tells me having 100 grams of hot water is just barely enough to melt 100 grams of ice. Just barely. And once it melts it, it doesn't have any energy left to heat it up beyond that. It's basically, that's all it can do. Melt it and some fraction of a degree warmer than that. So that ice is extremely powerful. Now I'm going to change this a little bit. I'm going to change this example and say, okay, instead of this, got 100 grams of ice, I'm going to go down to 20 grams of ice. We're going to do 20 grams of ice. I'm going to have 100 grams of water. Put water at 70 degrees. And let's throw a chunk of metal in there too. Let's say we're going to deal with the calorimeter now. We're going to say we have our calorimeter, 75 grams of aluminum is our calorimeter. And that's at whatever the temperature of the water is, which is 70. So we need to be careful we don't get too much ice because otherwise the ice is overwhelming to the whole thing. So now, again, same thing. Q for that plus Q for that plus Q for that. Some of them are going to be negative in terms of what they contribute. but 20 grams of ice, okay? Well, I gotta have Q for the melt and Q for the cold water. Those are both coming from the ice because it starts frozen and then it melts, and then we got cold water that needs heated up. This term, just that term, Q of the hot water. And this is just the aluminum, Q of the aluminum, Calor6. Again, Q of the melt, 79.7 times the mass in grams. Q of the cold water, I've got 20 grams of cold water. The C is 1, T minus 0. That takes care of these two terms. Q of the hot, I've got 100 times 1 times T minus 70. Q of the aluminum, I have 75 times 0.215 times T minus 70, and all of that together equals 0. This is 1594, I believe. Nope. All right. 16, yeah. All right, plus 20T plus 100T minus 7,000. .75 T minus 1102.5. And again, I'm going to add all those T's up, and I see 120, 135.75 T. Those negative guys, I'm going to add them up. I've got 8102.5, and then this one comes the other side as a subtraction, minus 1594. I think that's what I get there. And 6508.5 divided by T equals 47. 47.9. Round that into the math right. So even with only 20 grams, you look at this, 175 grams of other stuff starting at 70 degrees, and only 20 grams starting as ice, but it's still able to drop the temperature by 23 degrees. So drop the temperature effectively from as much as being at room temperature down to 0, down to freezing. That's how much it's able to drop that temperature with just 20 grams of ice. Now, in addition to this, we could have steam. We could have a problem. See, do I have a, yeah, I don't think I have an example here. But we could have a problem where we start with some steam, start with some water, start with some ice, all those things going together. We got some aluminum, we got some silver, we got whatever we're plugging into there. Each one of those terms is going to have a Q. And for steam, you're going to have a Q that accounts for the fact that steam has to condense into water. And that's going to be 540 times whatever the mass is. That's going to be one of your many terms. And then you're going to have hot water from the steam. The steam water is going to have to cool down. And when you do steam, if you think about that, so you're going to have T minus 100 for your hot water. And as the temperature cools down, that's going to be a negative. And therefore, the steam minus 540 is going to be a minus times whatever the mass is, because of the fact that they both have to have the same sign. They're both giving energy to the system. Okay, so let me do it. I'll set up an example like that. Let's just say we've got 10 grams of steam, which I know doesn't seem like much. And we'll put it at 100 degrees. Now, steam could be hotter than that. Hotter than 100. 100 is where it condenses or vaporizes, depending on which direction you're heading. But it can be warmer than that. The steam could start warmer. And if it starts as steam at 120 degrees or something like that, it's going to have to move 20 degrees before it gets to the point of condensing. And during that move of 20 degrees, it has a different specific heat than water does. And the same way with ice, we could have ice in the freezer, it could be negative 20 degrees, and it's going to have to warm up to 0 before it begins to melt. And so you have to take that into account, as you can have many terms coming out of just one item here. 10 grams of steam at 100. Let's say we got 500 grams of water at 20. And let's say we got a bigger calorimeter. Let's say 100 grams of aluminum in the calorimeter is also going to be sitting at 20. And let's see what happens with that. Now, so we got very little steam, right? Just a tiny bit. 600 grams of other stuff, 60 times as much, and 80 degrees colder. So let's see where that ends up. Now, we're going to have the Q of the condensation, condense, okay, plus the Q of the hot water that's formed from the steam, plus the Q of the cold water. Cold is relative, of course. This is much less than that. Plus the Q of the aluminum, which is the calorimeter. All of those together have to equal 0. And go ahead and do that. 10 times 540, and as I said, that's giving energy to the system. I'm going to put a minus sign in front of it. MC delta T, I got a mass. Well, I only got 10 grams here. Once it's water, it has a C of 1, and I'm doing T minus 100. My cold water, I've got 500 grams. Specific heat is 1, T minus 20. And my aluminum, I've got 100 grams, C of 0.215, and T minus 20 also. And all those together equal 0. So, that's what I get out of the steam. Those are the steam terms and the hot water terms. 500 T minus 10,000. And over here, 21.5 T minus 430. I'll check that. 2 times that is 43. Yeah. Okay, so that's what I get. Again, combining my terms, 500, 521, 531.5 T. The other ones, boy, I got a lot of negatives now. I got negative 10,000. 11,000, 16,400, 16,800. We're going to do the other side, 16,830, I believe. Double check that, 64, 16, oh yeah, 16,830. And so, last step, I'm dividing through by 531.5. Temperature of 31.5 degrees C. So what happened here? A little tiny bit of steam was able to heat 600 grams of stuff up by 10 degrees, even though it's just a little tiny amount of steam. If we had 100 grams of steam, we wouldn't even be able to condense it all with that much, because we'd be 10 times as powerful here. There's no way we'd have a number so much bigger here that we probably, when we divided, we'd probably get a number that was bigger than 100, saying you can't even cool that all down, which is a situation where you have partial condensation or partial melting. You can happen on either direction.